Hello, Memphis Communiversity. This is Quads here. I'm doing the particle motion worksheet. Like always, you can find a PDF of the worksheet and the answers in the video description. So before we get started, I just wanted to go over just an overview of what particle motion is. So it's a pretty broad topic, and it'll come up here and there throughout, like calculus things. And there's three main functions involved with particle motion: the position function, which is s of t, t being time, the velocity function, which is v of t, and the acceleration function, which is a of t. And so if you just imagine those like in order, then you have position function, and the derivative of position is velocity function, and the derivative of velocity is acceleration function. So this video, we're really only going to be doing the derivative side, so position to velocity to acceleration. You will come across backwards where you go acceleration to velocity to position, and that's dealing with integrals, and we do other videos in unit, like a later unit will have some of those. But yeah, so this is the most like physicsy part of calculus, and it's not too difficult. Mostly you're just going to be taking a derivative. There's just like specific things you have to do for the different kinds of questions, and you just have to remember like which one's which. So I'm not going to list the rules now, but we'll just talk about them as we go through it. And yeah, I think that's it. Okay, let's get started. So this is our position function for number one, and number one has like multiple different parts of it, so we're always going to come back to this position. So if we're looking for the velocity, remember it's position, velocity, acceleration. So that means velocity is the first derivative of position. So we're just going to take the derivative of this position function, and that's 3t squared minus 18t plus 24. And then we're just going to factor it. So we get 3 times t minus 2 times t minus 4. This next one is velocity after 3 seconds. So that means we're going to do v of 3. So we're just going to take, we already found the velocity function, and we're just going to plug in 3 now. So we got 3 times 1 times negative 1. That's 3 times 3 minus 2 times 3 minus 4. And we get negative 3. I don't know why I wrote an M. I think I probably meant, I don't know if the unit would be there. Miles per hour, I guess. Or it's 3 seconds, so miles per second. Yeah, meters per second. It's meters per second. Duh, it says meters in second. I'm sorry, guys. My bad. That's not the important part. The important part is negative 3. We're just going to move on. So now we're finding average velocity. This is different than velocity at a certain time. This is algebra slope. So if you remember, like, a derivative is it's calculus slope. It's basically the instantaneous slope, the slope of the tangent line at a certain point. We're just going to do the average velocity. So that just means we're going to take, our interval here is going to be 0 to 4 because it's the first 4 seconds. So we're just going to take the velocity at 4 and the velocity at 0. We're going to subtract and then divide. So we can, the position at each of those, and then we divide by 4. So remember, we go back to this position function. And we get, if you plug in 4, that's 4 cubed, minus 9 times 4 squared, plus 24 times 4 plus 2, and that's 18. And if you plug in 0, it's 0 minus 9 times 0 plus 24 times 0 plus 2. So that's where we get the 2. And then we divide by 4 because that's the length of the interval. And so this time I wrote the full unit, and our answer is 4 meters per second. So, yeah, that's 16 divided by 4 is 4. When the particle is at rest, if you remember, for something to be at rest, it's just not moving. So that means the velocity is 0. So whenever you see that, that's kind of like a keyword. So we're looking for when. So we're trying to find the t when it's 0. So we're just going to set it equal to 0. We already have it factored out, so we'll just take that and move it down here. And we get t equals 2 and 4. Now it gets a little trickier when we want to know when the particle is moving forward. So we're going to take these zeros that we already found, and we're going to make a sign chart. So draw a little number line, put your 2 and your 4 on there, and we're going to end up with a parabola shape for our sign chart, and that looks more like a V than a parabola, I'm sorry. And so to know when it's moving forward, that's a positive velocity. Because remember, velocity indicates direction too, so positive velocity is forward, and a negative velocity is backward. So we're just looking for when the velocity is positive. And remember, this is a velocity sign chart. So when v is greater than 0, I'll move. And that occurs between 0 and 2. And then after 4. And that's when we have our velocity moving forward. Yeah. So total distance is kind of a tricky one. We're going to draw that sign chart again, except for we're going to add 0 and 6 because those are our intervals here. So we're keeping the 2 zeros, and then we're just adding our endpoints, critical points, endpoints. And basically what we're going to do is we're going to break up this sign chart. So I have it drawn here. We're going to break it up into each of these 3 sections, and we're going to find the distance traveled in each section, and then we'll add them up. But we can't just do it all at once, because then with the different directions, it would like cancel each other out, and then we'd end up with displacement, not distance. So like if we go 5 feet forward and then 5 feet backward and then 5 feet forward, our total distance would be 15 feet, even though you're like only 5 feet away. So that means like that's why you have to do it in each 5-foot section. You have to like get the distance for each one. And so that's going to look like the absolute value of S of B minus S of A. So remember, S is the position function, and B, so just the later end of the segment. So like if we have the interval 0 to 2, we're going to be S of 2 minus S of 0. And it is absolute value, right, to cancel out those negatives in there, and to get all the actual distance, not the displacement. And so we're going to do that for each interval. So here we go. The first one is 0 to 2 is our first interval, this section. And that's going to be the absolute value of S of 2 minus S of 0. So remember, we're looking at our position function, which we saw earlier up here, given. So just pop right back up there. And then you're going to plug in 2. So that would be 2 to the third minus 9 times 2 squared plus 24, 2 plus 2. Is 22, and then when you plug in 0, so 0 cubed minus 9 times 0 squared plus 24 times 0 plus 2, we're just going to get 2. Also, I think I might have misspoken when I was speaking out the 2. I think I might have said 2 squared, but it's 2 cubed in the beginning. You'll figure it out. And so, let me move my face again. Actually, we're just going to we're going to put it in this corner for a second, because we're going to move up and down for a bit. So we get 20 meters for our first distance. And now we have 0 to 4. So S of 4 minus S of 2. And we're just going to pop back up to that function. So 4 cubed minus 9 times 4 squared plus 24 times 4 plus 2 gives you 18. And then we already did the 2. So we'll just move the 22 there, and we get 4 meters. Remember, it's absolute value, so that's why it's a positive 4. And then final segment, 4 to 6, we've already, 6 is first. So once again, look back at that position function. We've got 6 cubed minus 9 times 6 squared plus 24 times 6 plus 2. That gives us 38. And then we've already solved the 18. There's the function again. And that gives us 20 also. So then we add those 3 up. This slanted paper is more my natural state of writing. It takes a lot of effort for me to keep it straight the rest of the video. But our total distance there is 44 meters. So this time we're looking for acceleration. This is also simple. If you remember the order, it's position, velocity, acceleration, which means velocity is the first derivative of position, and acceleration is the first derivative of velocity and the second derivative of position. So since we're given the position function, we take that derivative twice, but we've also already solved for the velocity function before in this problem. So we can just take the derivative of what we already solved for velocity to be. So we took that here. Well, I guess it's easier in the, go back a second, 1 minute. I highlighted the wrong part, so it's easier in the non-factored form for sure. Yes, this is what we're taking the derivative. So that would be then 6t minus 18. And then you can factor that to 6t minus 3. And now we're going to plug in 5. We're going to do a of 5. So we found acceleration at time t, and now we're going to find it after 5 seconds. So 6 times 5 minus 3 gives us 12 meters per second squared, because it's acceleration. So it's actually both of these are answers. When I first was doing this, I felt like this was the only answer, but S squared at time t as well. Okay, so speeding up and slowing down. This one's fun. Not really. The biggest rule to follow, well, the first thing is that you have to have both velocity and acceleration. So we're going to get the sign chart of velocity, which we've already made. That looks more like a parabola, sorry. And then we need the sign chart of acceleration as well. You can't do it with just one or the other. And so we just solved what the acceleration function is. So we can make a sign chart. Our only zero is 3, and it's just a positive slope line there. So basically the rule for speeding up and slowing down is you want to find the intervals where velocity and acceleration have the same sign. So if you're moving in a positive direction and you're accelerating in a positive direction, then you're speeding up. And if you're moving in a negative direction and you're accelerating in that direction, you're speeding up just backwards. But let's say you're accelerating, you're driving in a positive direction but accelerating that way, your car is slowing down. So that means same signs is speeding up, different signs is slowing down. So first we can look for where it's speeding up, where the signs are the same. And sometimes it's easier to draw dotted lines because the intervals aren't always the same. Like obviously this one doesn't have a 3, this doesn't have the other ones, but you're gonna like basically add these like points in the number line so you can see which segments. So see, I have 2 to 3 because here it's negative and here it's negative, but I can't, between 3 and 4, this one's negative and this one's positive. So even though this number line, like the segment is 2 to 4, we were only actually putting 2 to 3 because it starts slowing down there. And then it's also speeding up from 4 on because they're both positive. So velocity and acceleration have the same sign, so it's speeding up. And then we're going to find where velocity and acceleration have different signs, which is just everywhere else. So that's 0 to 2 because we got positive, negative down here. And then 3 to 4, we got positive down here and negative up here. Different signs slowing down. Okay, so we're finally done with the first question, but that actually included so many different of those like specific instances I was talking about. So like you have the like when it's at rest or moving forward or when speeding up, slowing down, find the velocity, find it at this point. So there's all these different things, but most of them are pretty straightforward as you saw. So now this other side is going to have a few different questions, and instead of one with all the parts for the same function, we're just going to have a couple of different ones. So let's begin. Our position function is given to us here, and we're looking for a time t when the instantaneous velocity, which is the derivative, also known as the calc slope. Remember, that's the slope of the tangent line at a certain point. So it's like at that point in time, it's instantaneous. And we're finding when that's equal to the average velocity, which if you remember from the page before, that's the algebra slope. That's the kind of slope you learned in middle school. Yeah. So we're first going to find this algebra slope. So that's s of 5 minus s of 0, because our interval is 0 to 5, divided by 5. And plug in 5 up here, so 5 squared minus 2 times 5 minus 10. And then minus 0 squared minus 2 times 0 minus 10. And we get 3. So 3 is our average velocity. And now we're looking for a time when the derivative is equal to 3. So we're going to set average velocity equal to instantaneous velocity. 3 is now equal to our instantaneous velocity. Now we should define what that is. So we know we need to take the slope. So that would be of the position function. So that would be 2t minus 2. And we have that set equal to the average, the algebra slope. And from there, we can solve that t equals 5 halves. So at 5 halves, the derivative is 3, and the average velocity for the whole thing is 3. So we found where they're equal. Let's see. A particle traveling along a straight line here's our position function. At t equals 1, is it speeding up or slowing down? So remember, for speeding up and slowing down, you need two things, velocity and acceleration. So this time we're not going to do a full sign chart because it's asking just at t equals 1. So we don't need to find like all the intervals in which it's speeding up or slowing down. We're just asking at that point in time, do they have the same sign, speeding up, or do they have a different sign, slowing down? So first we're going to take velocity of at t equals 1. So that's the first derivative here, which gives us pi cosine pi times t minus 2t. And if you don't remember, cosine pi is negative 1. And this pi comes from the chain rule. So that's pi times negative 1 minus 2. So we got negative pi minus 2, and that is less than 0. So so the velocity at t equals 1 is negative. Remember, we're really just looking for the signs for velocity and the sign for acceleration. So now we're doing acceleration at 1. So now we have negative pi squared, because of that chain rule again, sine pi t minus 2. And then we're going to plug in that t equals 1. So negative pi squared, and then if you remember, sine of pi is 0. So that's times 0 minus 2, and we just get negative 2. And that's also negative, which means both acceleration and velocity at t equals 1 are negative. So since the signs are the same at that moment, then it's speeding up the particle is speeding up at that moment. And just go ahead and write that little justification. They have the same sign at t equals 1, so the particle is speeding up. All right, we're looking for a maximum height, which if you translate that, remember height would be referring to its position, so we're basically looking for the absolute maximum of the position function. So when we have absolute maximum, first thing is locate the function. Like I said, it's the maximum height, so it's the maximum of the position function. So our locate function step is just s of t equals 32t minus 16t squared. our next step is to take the critical points. So remember, we're going to take the derivative of that and set it equal to 0, and then figure out what t is. So our derivative here is 32 minus 32t. And I just went ahead and wrote s prime of t equals v of t. It's not really important. The most important thing is that you're taking the derivative of this, so it might be more like easy for organization just to write s prime of t. I write both. You could just write v of t, whatever you want. Set that equal to 0, and we get t equals 1. This time, since we don't have intervals, we can't draw a table, or we don't have endpoints. In the normal 3-step process, which I made a video on, so go check out my other video if you don't know what I'm talking about. The third step is to make a table, and that's the endpoints and the critical points that are within those endpoints. We don't have endpoints, so this is a little different. So we're basically just going to draw a sign chart with that 1 point, and that's going to be a negative slope in this case. So just do your normal sign chart process for that. And so now we're going to write this long justification. So I'm going to wait for my hand to write it out, and then I'm going to explain it because it's a little tricky. Basically, it's just describing what this sign chart is. So I'll just go ahead and start. Actually, no. I moved the paper when I write, so I'll just wait. Okay, so, I gotta move my hand. I'll just wait for myself to finish writing it. I gotta learn how to write with my hand out of the way more. I'm sorry, guys. Okay, now that we have that back in the picture. Okay, so here's our justification. Since s prime of t is greater than 0 for t is greater than 0, greater than or equal to 0, and less than 1. So that's this. Remember, this is the sign chart for s prime of t, because our 0 is 1 right here. So s prime of t, this is our sign chart for s prime of t. S prime of t is greater than 0. It's positive. For t is greater than or equal to 0, because this is particle motion, so time is never going to be below 0 because it's like real life physics. So this is between 0 and 1. And s prime of t is negative, it's less than 0, for t is greater than 1. So that basically means if the derivative of position is positive, then remember position is increasing. And if the derivative of position is negative, then position is decreasing. So basically what we have is this instance where position is increasing, gets to 1, and then it starts decreasing, and we know this is the only critical point, which means it's not going to go like this a bunch of times. It's increasing, decreasing, and that's the only time it changes. Which means we know that 1 has to be the absolute maximum, because just think like increasing constantly, or not like at a constant rate, but it's only increasing until suddenly it's only decreasing. That's going to be your absolute maximum right there. So we know it occurs at t equals 1. And then we need to know, well, what's the value of it at t equals 1? The question asks, what is the maximum height? So first we figured out that the maximum height happens a second after you throw it, but we need to know what the height is. So then we just plug it into this position function. So we have s of 1. What is the position at t equals 1? And we get 32 minus 16, and the answer is 16. So our maximum height reached by the ball is going to be 16 feet. And you do have to write out this whole justification. In the normal 3-step process with the table, that kind of like acts as your justification. Not in this one. You have to explain what this sign chart means. And so basically, the derivative is positive while t is less than 1, and it's negative while t is greater than 1, so the absolute maximum happens at 1. So that's just one you're going to have to get like used to writing, and you're going to have to like practice. It's kind of weird. I call this the alternative way, and every time I'd come back to study for a test or for like the AP exam, I just forgot how to do alternative way every time. And it's like not even that complicated. It just would leave my brain. So if that happens to you, you're not alone. And now we are on our last question. Yay. Okay. We're looking to see if these two particles are moving towards each other or away from each other. Rookie mistake, people usually think that just the velocity tells you that, because after all, velocity tells you direction. But we actually have to know where the particles are starting from. Because let's say this is like particle A and B, and they're moving, they have their velocities different signs, and they're moving toward each other. Great. But what happens if they start right here, and they have velocity different signs? They're moving away from each other, right? Like toward each other, away from each other. So just the velocity is not enough to tell you if they're moving towards each other, away from each other. Kind of like earlier for speeding up and slowing down, like just the acceleration doesn't tell you that because it depends on what direction you were moving in the first place. For this one, you have to have, instead of having both V and A, this time you need both S and V. And it's asking specifically at t equals 3. So we're going to find the position of A at 3 seconds, and we're going to find the position of B at 3 seconds, and we're going to find the direction that they're each moving in at 3 seconds. So that's 4 different numbers we got to get. So I like to underline the position functions because it helps me like go back to them. So our first step is the position of particle A at 3 seconds, which we're just going to plug right into that position function. So that's 3 squared minus 8 times 3 plus 1. This time I actually wrote out the steps. Wow. And that equals negative 14. And then we're going to get the velocity. So we know it's starting at negative 14. What direction is it moving in? The velocity at 3, so take the derivative of that position function, and we get 2t minus 8, plug in 3, and you get negative 2. So now we're just going to go ahead and find position of B at 3. Here's this function. Remember, it's a different function, so make sure you use the other function. 3 squared plus 2 times 3 minus 4. And I didn't write what that equals, but it equals 11. And then let me move this. You take the derivative of that, so that's 2t plus 2, and we'll plug in 3, and we get 8. So now we're going to draw a number line because visuals are really helpful in this. So our starting positions are negative 14 and 11, which I didn't write, but that's what it is. You can only kind of see it, but it does say 11 down there. So this is particle A, this is particle B. Now we want to know what direction are they going in. The actual speed part, the 2 and the 8, the volume, I guess, of the velocity is irrelevant. We only want to know the direction, so we just really need to know the sign. So particle A is negative 2, which means it's moving backwards, going to the left. So it's starting here and moving to the left because velocity is less than 0. And B, it's 8, so it's positive, so it's moving to the right. And so now you can really clearly see that A and B are moving away from each other. Imagine if they started on the other side of each other. They'd be moving toward each other. That's why position is so important. We just need to write out our final answers. At t equals 3, particles A and B are moving away from each other. And we plug 3 into all 4 of those because it's happening at time t equals 3. So that's it for the worksheet. Particle motion, eventually you'll do some backwards with integrals. So all of ours were either position to velocity or velocity to acceleration or position to acceleration. But when you start doing integrals, you can do acceleration to velocity, velocity to position, acceleration to position. And so we have those two. You're going to want to look for particle motion videos that aren't like this set of videos. And we have some videos also that are going to be practicing real particle motion questions from the AP exam, but just broad ones taken from the AP exam. So that will include both derivatives and integrals. So it's not like a unit lesson like this one is. And yeah, we have review videos for particle motion in the advanced derivative playlist because this is considered an advanced derivative topic. And I think that's it. So You know what to do if this video is helpful. Like and subscribe, and you can find a ton of other helpful videos by girls doing math. Like I said, that absolute maximum normal process, I did that one. Check it out, quick plug. I really hope this is helpful. Remember that you can post questions in the comment section, and we also have a Discord server in the description where you can put your own calculus questions or ACT questions. Have an amazing day, and good luck with particle motion.